The ideas. First, the orthonormal basis, the cleanest kind of basis to work with. Second, more of Dirac's beautiful bracket notation. And third, measurement, the rule that turns a quantum state's coefficients into real probabilities. Let's begin. Let's remember where we are. A vector is a state, and a basis is a set of basis vectors that build every vector in a space. X hat and Y hat span a flat plane, 2 dimensions. Add Z hat, and you span 3-dimensional space. And even an n-dimensional space simply has n basis vectors, v0 up to v, n-1, spanning everything. Bases don't have to be arrows. The number of eggs has a 1-egg basis. An electron's spin has the basis spin up and spin down, so spin space is 2-dimensional, just 2 basis states. It feels like a flat 2D plane, with one difference. In a real plane the coefficients are real numbers, but in spin space they may be complex. We lean on the simple case to understand the strange one. Now the star of the chapter, the orthonormal basis. Its definition is one tidy line. The inner product of basis vector vi with vj equals 1 when I equals j, and 0 when they differ. We write that compactly as the Kronecker delta, delta ij. That single equation hides 2 beautiful conditions. Those 2 conditions are these. When I equals j, each basis vector dotted with itself gives 1, so every basis vector has length 1. We call that normalized. When I differs from j, the inner product is 0, so the vectors are orthogonal, sharing nothing. Orthogonal plus normalized gives the word orthonormal. This is easy to feel in our 2D plane. What is x hat dotted with y hat? 0, because they're perpendicular, neither contains any part of the other. And x hat dotted with itself? 1, because a vector contains 100% of itself. A little joke from the book: if you want to date someone, tell them you have a non-zero inner product. Picture 2 candidate bases for the plane. On the left, x hat and y hat sit at 90 degrees, a clean orthonormal basis. On the right, x hat and a tilted y prime sit at only 45 degrees. Since the cosine of 45 degrees isn't 0, their inner product isn't 0, so they overlap. That basis is not orthonormal. Here's a subtle point. The neat row times column way of taking an inner product only works in an orthonormal basis. In the x hat, y hat basis, x hat is the column 1, 0, and y hat is 0, 1. Multiply them as a row by a column. 1 times 0 plus 0 times 1 equals 0. Orthogonal, exactly as expected. The math agrees. But try the same trick in the non-orthonormal x hat, y prime basis. Writing y prime as the column 0, 1 and multiplying would again give 0, suggesting they're orthogonal. Yet we know they sit at 45 degrees and are not. The column shortcut lied, because we used it on the wrong kind of basis. So in this book, we always work with orthonormal bases. Now let's sharpen the notation. Any vector, any state, can be written as a ket, a vertical bar and the name inside an angle bracket. If vector A equals vector B plus vector C, we simply write ket A equals ket B plus ket circa, and if A equals M times B plus N times C, then ket A equals M ket B plus N ket C. The notation just carries the vector algebra along. Every ket has a partner called a bra, written with the angle bracket on the left. Kets and bras live in 2 mirror worlds called dual spaces, and each ket maps to exactly 1 bra. The recipe: transpose the column into a row, then take the complex conjugate. So if ket v1 is the column 1 plus 2i, and I, then bra v1 is the row 1 minus 2i and minus I. Now watch this fit together. The inner product of v1 and v2 is the bra of v1 written beside the ket of v2, a star c plus b star d. Written out, it reads bra v1, ket v2, which we shorten to angle v1, v2. The word bracket splits into bra and ket. That, at last, is why the notation has its name. Let's do one in 3 dimensions. Take ket VA with entries A0, A1, A2, and ket VB with B0, B1, B2. To form the bra VB, ket VA, we transpose VB into a row and conjugate it, then multiply. The result is A0 B0 star, plus A1 B1 star, plus A2 B2 star. Same pattern, one more dimension. Let's not get lost in algebra. Remember, every vector is a state of a real system. Take electron spin, with basis states spin up and spin down, which we draw as the arrows up and down. The basis states are themselves vectors. Spin up is the column 1, 0, and spin down is 0, 1. We don't need to know what spin truly is to use them, just as we trust atoms, or a single egg. So any electron spin state is a superposition, a linear combination of the two basis states. Ket psi equals alpha ket up plus beta ket down. It genuinely carries an up part and a down part at once. But up and down are orthogonal, they cannot both be fully true. To learn which it is, we must measure. When we measure, the superposition collapses, at random, to a single basis state, up or down. The chance is not arbitrary. The probability of collapsing to up is proportional to the magnitude of alpha squared, and to down, the magnitude of beta squared. This is the Born rule, the deep meaning of those coefficients, and the heart of the Copenhagen interpretation. What is the magnitude of a coefficient squared? For aj, it's aj star times aj. Say aj equals 1 plus I. Its conjugate is 1 minus I, and their product is 1 plus 1, which is 2. And indeed the length of 1 plus I is root 2, whose square is 2. So the magnitude squared is always a clean, real, positive number, perfect for a probability. For probabilities to behave, the state must be normalized, it must have length 1. Length comes from a vector's inner product with itself, bra v, ket v, which equals the sum over I of the magnitude of ai squared. Setting that whole sum equal to 1 is exactly the normalization condition. A normalized state is one whose pieces of probability add up to a perfect whole. And now the payoff. Because the state is normalized, the proportionality becomes an equality. The probability of collapsing to basis state Vi is exactly the magnitude of ai squared, ai star ai. If a vector isn't normalized, we simply divide it by its length, the square root of bra v ket v, and it becomes normalized, ready to read as probabilities.
वीडियोस बनाने हैं, फिल्मोरा है ना।